and AES. Okay. She established general methods to predict surface segregation of substrate elements and layered structures, and to predict interface terminating elements in metal oxide interfaces. She also worked on measurements of work functions and predictions of general relationship between work functions and compositions of materials. Through the development of general prediction method, she realized the importance of interdisciplinary use of scientific knowledge. I'm sure all of us actually today, realize the importance of interdisciplinary scientific knowledge. She has started working on natural language processing for computational use for scientific knowledge. She was a visiting scientist in National Institute of Standards and Technology, USA, between 1992 and 1993. She was an adjunct professor of Charles University of Czech Republic for several years. She is a part-time professor and graduate of School of Tsukuba University. She also honored as MANA scientist, Nano Electronic Materials Unit, Semiconductor Device Materials Group, NIMS. Okay. She has a substantially large number of publications, which is as high as 170 plus publications. And her citations are really impressive, 1,137. And I'm sure it is only increasing. Okay. So we welcome Dr. Michiko Yoshitake. She is from National Institute of Material Science, Japan. And our topic for today is natural language processing for material science. We have 45 minutes. We will try to, I will give you or one of us will give you a signal just about 5 minutes before the end of the talk. Yes, it's all over to you, Dr. Michiko. Thank you.
Thank you very much for the introduction. And can you see the view graph?
I can see you.
No, I see. And then wait a moment.
Yeah.
Why it doesn't work?
Madheshwara?
Sir? She can share actually.
Yeah, you can, I think you need to share your slides.
Yeah, we make
because it did come actually earlier.
Ma'am, if you have already in the presentation screen, so you have to come out the presentation screen, then share it again.
Yeah.
Alright, so it's
no, please escape from presentation mode, ma'am.
Escape. Okay.
Yeah, then and then share it again.
And reload. Yeah.
Can you see the slide? No.
No. First escape from slide mode.
Yes, I escaped, but
and then share the file.
Maybe, yeah, I have to go for the share. Okay, this is a tool. Okay, let's see. All right.
Yeah, now it's coming.
Yeah.
Okay,
yes.
We have you. Yes. Yeah. Proceed.
This is a slide. Can you see?
Yeah, yes, ma'am.
Yes, we can see.
Okay.
Yeah.
First of all, I'd like to thank the organizer for inviting me to this nice conference and giving me opportunity to present a research field we have newly started. It's a really newly started topic. Because the topic is quite unique in the conference, I'd like to start with the background why I came to this new field. The talk will be structured like this, we graph, and wait a moment. After this brief introduction, I first talk about the data-driven research and material informatics, because this natural language processing is a part of informatics technique. And then what this natural language processing is, It's really quite new for most of the audience, I think. And then some basic approach in natural language processing, especially the part which is not common with usual machine learning. And then I talk about some applications for this natural language processing for material science, which is quite a few at the moment. And then I will talk about our trial, because at the present point, the already established technique are not satisfactory for what we want to do. First, as the chairman introduced, I worked on this material science course, and I worked on surface segregation of underlayer elements. In all days, 30, 40 years ago, people are puzzled by the phenomenon that gold film is deposited on silicon and anneal. Then the silicon migrates on the surface of gold and segregates like this. This is a kind of schematic cross-section of the sample. And also, if the tantalum thin layer is inserted between silicon and copper for prevent the interdiffusion between copper and silicon, by annealing tantalum migrates on the surface of copper, and then it also with the preceding procedure, due to this phenomenon, copper migrates to silicon and interreaction occurs. Many people are puzzled why it happens and in which combination of material it happens. So I tried to make many combinations of substrate and film and observe the phenomena. And I came to conclusion that we can make up the general equation, a kind of equation to predict for most of the all materials if the substrate or the underlayer element segregation occurs or not. This prediction already is given as a software in our website, which I will talk about later. And the next thing is I worked on the metal oxide interface. If you have the interface between metal and oxide, oxide composed of metal element and oxygen atoms. The interface could be either oxygen at the interface or the metal atom at the interface. And this difference makes a huge difference in many properties like wetting or band alignment, which is a key to improve the power consumption of electric device and so on. By this segregation prediction or the interface chemical bond prediction is provided as software in our institute website, mapping database system, MapNav, and if you scroll down, you will find this application category, and here is surface segregation, and this is interface bond prediction both, and you will see such a screen that by putting this substrate element, choose from this periodic table, and then choose the environment for the atmosphere of needing. Then the by pushing the button, calculate the result if the segregation occurs or not. It's shown on the screen, and the nearly almost 5,000 combinations can be simulated with this software. And for interface bonding with between pure metal and oxide, or the binary alloy and oxide is given. And again, choosing the metal element or oxide from the period table, it will give the result by pushing calculate. If the copper, pure copper with aluminum interface, oxygen is terminating. But if the aluminum is alloyed with copper or metal element, the interface becomes aluminum, which we already proved by experiments. In the process that we think about these kind of things, I need to think how this segregation is determined, which property is important for prediction and so on. And this is another example of such thinking when I predict the work function, which is a very important property for electrical device, which Schottky very high, and which result in the power consumption. And in some material like transition metal carbides and nitrides, we found that by seeing viscous hardness is a mechanical property of material. But by seeing this viscous hardness, we are able to predict work function. And this is the network type of knowledge connection, that work function is determined by this is determined this by like this, and the tensile strength is proportional to viscous hardness and so on, which I found from textbooks from different fields. But surface physics, it's my specific field, so I don't need, but for this kind of thing, I need to look at the textbook. And then I thought that if the computer can automatically find such a relation, it's nice. I'm not able to really read each by each. That's why I'm trying to work on natural language processing. And before I go into natural language processing, I'd like to talk about this data-driven or material informatics. It was started in 2011 when the US government launched the material genome initiatives. After this, other European countries, China, Korea, Singapore, so on, followed with this movement towards Japan. And the idea is to produce huge amount of scientific data via high throughput automatic synthesis, measurement, and theoretical calculations, and then treat those huge data. In this case, it's a numerical data, like density is blah, blah, reflection index is blah, blah, or something like that, with machine learning and a neural network. And as a part, it's like a very small part, but extract scientific information from text data is also a part of material informatics, and then which we are working on. And this text data analysis is used in business a lot in practice, as well as the numerical data analysis or the image analysis like face recognition. The text data is used for chatbot and translation, language translation, and so on. And then I will go for what is natural language processing is. This is technique to make the computer use, but looks it uses natural language as human. And you can, it makes computer can extract the abstract or the make sentence and so on. Now we say natural languages. This is the language that are naturally developed. And contrast is a formal language, which is actually made under clear rules, like programming languages, markup languages, something like that. Usually, if you say here language, maybe people think of natural language, I suppose. This natural language is applied for chatbot, translations, and the news writing, summary making, and so on by a computer, like now. But not much in material science, unfortunately. But the technique on natural language processing has improved a lot quite recent, because the text is written in electronically, so that the digital documents are impossible to analyze, and also the computer power become very huge, and then now it can handle very huge computation. Actually, the language is need more than usual numerical data processing. And how computer can handle languages? Well, it recognizes letter in the computer as a code. So the letter is converted into number in some way. And the word, something like how, has to be converted in another way, in some way. And how can computers handle language if sentences are there? This sentence has to be converted into a number in some way. Once the words or sentence is converted into numbers, then it is basically same as numerical data handling in machine learning. So one of the very big issue on natural language processing is find a good way to convert word or sentence into numbers which reflect meaning of words or sentence. And this is some basic approaches for making convert word or sentence into numbers which cause some kind of meanings. And this is handmade. we just don't care about it. And basically two ways: so-called count model, count-based model, and predictive model, both for words and sentences, and for making the sentence into numbers. There are different types of predictive model that makes those representative technique. And last person for sentence is a bit different way, which uses grammar. Firstly, I talk about the need, how to make the words into number by count-based model. If we have a couple is a good electric conductor and a good heat conductor, then they make a table like this, so that here is the list of words used in the sentence. Couple is a good electric conductor, and a good is here, so we don't need this word. Heat conductor is here, so we don't need that. So this is how many kinds of word is used in the sentence. And if the couple has the neighboring word is, so couple is one, and then the other is 0. And the good has a neighboring word up 2 times, and the electric 1 time, and heat 1 time. Well, you can go this way or this way. It's symmetric. And this row of numbers, good for good, it's a vector of good word, good. And conductor, this row of numbers is a vector of conductor. Then you can calculate cosine angle by this way, that this is very limited number of words, but if you do it very huge database, you can get by this way that similar word has small angle, cosine angle. That's the basic way. And the predictive way is a bit different. This is a neural network to predict the words if the neighboring words is given, but it's the center word is. And first, we mix a list of words, and then by putting value 1 to the word, each word, so it's very symmetric one, only in this one, in this direction. And this kind of vector is called one-hot encoding. And then insert such a vector. For example, this is good vector. This is vector for conductor. And then they have to predict electric is the answer. So make a neural network to predict electric from good and conductor input. This is the continuous bag of words type prediction, and there's another way that gives the center word and predicts neighboring words, but the way is just similar. You predict, you put in a word electric, and the output is good and conductor. And then by doing this, here it becomes a matrix of weight that each number goes to some converted into some numbers by the feedback of answer level. And this vector, this matrix component is used as a vector of each word. For example, the copper vector is 0.1, 6.3, 2.8 or something. By this way, again, the word is vectorized and the word similarity is given by the cosine angle between two vectors. This is a way how they convert the words into numbers. Actually, the row of numbers vector. And the famous example is given by Google that the queen equal king minus men plus woman. By this kind of way, one can get a vector for king, vector for man, vector for woman, vector for queen. Then one can find the relation between vectors like this. And that's what the Google gave. And this gives really sensation in 2013 or something. And this technique is now very often used in the background of natural language processing. And this kind of conversion word into number is generally called word embedding. And this word embedding technique is used for any of the natural language processing. The second one is how to get the meaning of sentence into number or row of numbers. For example, there are also count-based and prediction-based, and we first go to count-based. And there are two main methods called bag of words and term frequency inverse document frequency method. And first I talk about the bag of words. For example, there's a sentence like 1, 2, 3, 4, and just list the words like before and put the number which is used in sentence 1, 2, 3, 4, and just make these numbers as a vector, the component of the vector, and this is the vector of sentence 1. It's a very simple way. And with this vector for sentence 1 and vector of sentence 3, it's like this. And then if you compare those four vectors by cosine angle, one can see that most close to 1 is the sentence number 3. If you do it more huge number of sentences, you can find the which sentence say similar things, or which sentence talk about completely different matter or something. And the term frequency and invert document frequency is another technique to make the sentence in number or to capture the characteristics of sentence. And it's a bit too complicated, but one is that a word T is how many times appearing in a document D. So it suppose that this term word is important in the sentence, in the document. And another one is that the whole number of documents N, how many documents include that word T. It means that this is inverse, so that if this is large, means that a word T is included in most all documents. It means that this word appears often, but doesn't mean doesn't represent its characteristic of a document. Well, with using these sentences that I used before, you can make such a table by the previous definition, and it's complicated, but by this method, it's two numbers has to be multiplied, so that it says that the important word for sentence number one is electric. Important word for the sentence 3 is unique and important is aluminum, and the important word in sentence 4 is insulator. And this kind of technique is used to divide sentences, documents into groups, so that the similar words are important in those documents, and another important word for another documents, and so on. And the documents clustering and so on are done in this way. And another one is so-called doc-to-deck, is similar to word-to-deck for word meaning. It is to predict either the neighboring or the center word using word ID. Doc-to uses the similar, but put some document ID at the beginning. It can be anything, but you have an answer here by back propagation. This is a deep learning word, but by using this technique, you can get the document ID. And document ID is supposed to show some meaning of the document. And so far, this kind of technique, sentence is made into a vector that present a kind of meaning sentence, but there's no sequence in consideration. The sequence of words are considered in this kind of technique. So the so-called recurrent neural network is used to analyze the next step. And this recurrent neural network itself is used for the usual deep learning method for numerical analysis, like time sequence, numerical data, and so on. But because we use the word, we have this part, word embedding part, and after we get the result, we also have to bring back to language from numerical results. So this kind of neural network can be symbolically written like this copper goes embedding numerical data and the neural network here. And then after this neural network, it has to be deconverted to, so you convert copper by numerical data, so we have to do the reverse. It's called affine. And then this is the, which is most probable to find, which is most probable one. Like the probability, this gives the probability, but the answer is only one, and most probable one. So this is just to choose the most probable one. And if you think previous network is like this, then the RNN, recurrent neural network, is something that if you have the input of copper, then the next sentence, next word is supposed to be is. And then you put is as an input and use the same this neural network to get the most probable one as the next one, and so on. This is the prediction of next word, so that it's a sequential to find the word. And this also is very nice technique which was developed at the beginning, but soon it became obvious that the simple, this one, forget very quickly or previous words. So long short-term memory, so that the computer has to memorize long-term, so that the word which is a part has to be memorized. And also the in natural language, there's a phrase like a boy wearing a cap is my brother. So this wearing a cap is explaining a boy. So it's backward sequence, so inverse time sequence has to be taken into account. And with this, there's a technique by directional long short-term memory. It's also the words for deep learning, and the previous model with RNN looks like this, but it's inside it's this one. And to make it long short-term memory, it has a forget gate, or the output gate and the input gate. So the once forgetted memory has to somehow recover or something like that. Very tricky way, but and very complicated network. But it worked quite well. Actually, we tried this for our purpose, and got some result, which we will show at the last part of my talk. and but as you see, this is very complicated one, and time and computer resource takes a huge load. Now, then the Google again developed the paper, published the paper, attention is all you need. And instead of this complicated LSTM layer, they developed the so-called self-attention layer. And this makes the Google Translator improve a lot in 2016, November. And this is a bit complicated, so that I wouldn't go into, but the attention means that they don't treat all words evenly, but make the matrix which suggests which word is important. What can I do to see this? I don't know. Someone raised the hand. Sorry, I just continue. Well, without this is N, but it masks the word randomly, and then they predict this masked word. This to the layer to do is called self-attention layer, and not with sequential network, recurrent neural network, and they run the sequence in a way. And this is called BART, and but you can see how many, this is a million, 800 million plus 2,500 million words, makes 3.3 billion words they use for training the network. And this is really huge data and needs huge computer resources actually. But because it worked very well, people followed to make so-called BioBird or SciBird using learning text from this previous corpus plus PubMed medical abstract, and also this is also some medical articles. And SciBird is for computer science plus biomedical documents using such a huge corpus they made. And also there's a Japanese bird and other many modifications are already published. The another one is parsing, which uses only the, which is very difficult, different from machine learning usually. And those sentence is made in part of stitch tagging, so that it's noun or verb or preposition or article, they predict. It's a kind of prediction also, and then making a structure. For example, copper is a conductor. At the beginning, if the word copper comes, which kind of part of speech it should be, and the connecting which is predicted by optimizing by hidden Markov model with BW algorithm This is maybe also new, I think, for many people, but which is the most probable computer can calculate and find. This is a basic idea. And after this is noun, verb, particular noun, it's fixed. Then also the tree, the computer can make any structural tree of connections. And then again, its probability is calculated and find the most probable structure. And
Yes,
now
can you hear me, Doctor? We have about 5 minutes for your presentation.
yes, I think it's okay.
Okay, fine, thank you.
Yeah.
Please go ahead.
Yeah. Now the first thing is very accurate, so can use. And then the last part is about the application of material science. Actually, if we Google or Yahoo, the material science natural language processing, you with Scholar, no hits. And the Yahoo top 10 is like this. And actually, most of them are about mat2bake. It's a material science based word2bake application. And if we search also with Google, the same top 10 is the same page with the full search. And among this, the only word2bake has been used for users with respect for the developer. And so I explain what is mat2bake. It's a model of word2bake. I explain with focus the text used for neural network from material science, especially inorganic materials. And what they found is that if you have element and vector for zirconium, chromium, nickel, or the vector for zirconium oxide, chromium oxide, and oxide, and also the vector for its structure, like HCP or BCC or something, and they have some common feature that this direction of the vector shows oxide of this. So if you have metal and then draw the vector for this direction, there would be the vector for oxide of this material. And if you go this direction, the vector of this here is the structure of the vector. The last, I talk about our trial quickly. We would like to extract knowledge from textbook. So the ratio between the knowledge that example is this relationship that the ratio between thermal conductivity and the electroconductivity of materials are proportional to temperature T. The ratio, so under the same temperature, thermal conductivity is relational to proportional to electric conductivity. To do this, we have worked embedding with material science related books and so on, and give training data such as this is proportional this or something, and then like this. And then by using bidirectional STM, computer extract this is something with this or something like this. And this successful case is grammatically correct. And there are also failure cases, which is completely mess. And unfortunately, grammatically correct, even if it's grammatically correct, there are nouns which are not entity we would like to extract. And making this training data, we first to tell the computer which is the right answer. This is handmade, very laborious. So now we are trying to other techniques. And the important thing about natural process and language processing is the appropriate bus, prepare the appropriate bus corpus, and use not only one module, but proper combination of various modules is very important, and combine different types of machine learning technique is important. Very complicated compared to image processing, unfortunately, but still, that's why it's still under development, I suppose. Thank you very much for the listening to my talk, and I'd like to acknowledge Vellore Institute of Technology and this conference organizer and especially Professor Madiswaran, who invited me. Thank you very much for your attention.
Yes, thank you, Professor Michiko. That was quite an enlightening presentation on how we can actually, work with natural language processing and machine learning or deep learning and using neural network this thing. There are a few questions. Madheshwaran,
Yes, sir. Yes, sir.
the question? Yeah, do we read out the question or they will? She can see.
No, sir. You can read. If you can read, sir. Otherwise, I can.
Yeah,
read.
I can. Okay. So there are a couple of questions, Dr. Michiko. Can I read it out to you? Yeah. How the vector is important in natural language processing?
Oh, well, the computer only can handle numerical data.
Okay. Okay.
So everything has to be, well, in principle, the computer works with 0 or 1.
Okay.
Finally.
That's
so in any ways, you have to bring back, well, but if once it becomes numbers, then there's already a way to make it 1 over 0. So
okay. So for finally, it is actually converted into digital ones or zeros. That is what you're trying to say. But there is a weightage factor on, whether, it has been converted correctly to the, and that is going to be the magnitude of the vectors, I presume.
Magnitude of the vector.
Yes. See, because if we are going to, you showed A dot B is equal to AB, the cosine factor. Yeah.
Like this?
Yeah, fine.
This is, well, if the vector, well, there's a defect on this discussion,
yes.
I know. But if for example, if the vector of aluminum, magnesium, sodium, or something is correctly vectorized, it is supposed that the vector comes near, so that the cosine angle is closer than the vector.
Yes, so angle is closer. Yes, yeah, exactly.
Than the vector like polymers.
Okay.
Yeah, that's the idea of this cosine sentence similarity or word similarity by this cosine angle.
Okay, fine. So since you are using neural networks, I mean, just addition to this particular question, what kind of accuracies are we looking at? Okay, we are using a recurrent neural network. Can we talk about 90% or 95% accuracies in?
Well, it depends what you are going to do and what you would like
Okay.
to
Okay.
get, but
Yeah.
in any of neural network,
Yeah.
usually we have a set of the training data, and
Okay.
among this training data, 100%, we use 70% to 90% for training, and the
Okay.
rest
Okay.
for
Yeah.
testing. And after trained with this 70% or 80% of data, making a neural network models, and then they put this untrained data, rest of the data, 10% or the 30%, and
Okay.
then see if how much the corrective answer is
Okay. Okay.
gained. This is
Okay.
usually given as an accuracy in machine
Okay.
learning. Yeah.
Okay. Okay. That's fine. Okay. We have another question. Are you going to do this a priori or take the experimental results and then extend the idea to newer materials?
Well,
Do you?
I'm not really trying to trying to find a new material.
Okay.
What we are trying to do is that it's another topic that I actually am doing, but for example, if we find such an connections, then we are able to find what to do to go the right direction, not the material, but where to go, where to direct.
Okay. Okay. So you need to do a lot of say experimentation before you can actually come up with the right kind of pathway to reach the right language. Yeah. Is that
right
what it is?
Yes, that is
okay. Okay. Then there's another question. NLP is being done for various regional and international languages. Okay. According to you, which language was relatively easier and less tedious to process compared to others? Do you have a comparison? Yes.
Well, I actually didn't compare, but there are many such comparison. Or before you do the comparison, it's quite obvious. The English.
Okay. Yes, obvious. Yeah. Okay.
Yeah, it is very obvious. Yeah.
Yeah. That is true. Okay. So how much does grammatical structure of the language impact your NLP? Grammatical structure. I mean, is
parsing.
Okay.
Well, actually, right now we are working on this parsing technique, but the only parsing itself doesn't work quite well. So we have connected many techniques based on deep learning method and the parsing method combined.
See, because I think English language has a certain kind of grammatical structure. A language like Japanese or Indian languages have a slightly different kind of grammatical structure. So does that mean that we have to change the entire process of processing? That is what I would like to know. Do we, or it is just that your current protocol that you have presented works without the grammatical structure coming into the picture?
Well, for neural network type of work technique, it's not the grammatical structure. It's not including at all.
Okay, fine.
In principle, but because for example, especially for this RNN type or birth type, it considers the sequence of language So
Okay.
due to this sequence, its grammatical matter is somehow included as a hidden layer.
Okay. 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 So I think with that, we will thank Dr. Michiko for a wonderful presentation and for joining us, spending some time with us. We hope that you can actually visit us sometime
Thank you very
in
much.
the near future.
Yeah.
Okay. Thank you, Dr. Michiko, for such
Thank
a
you, Dr. Michiko,
Thank you,
and
thank you very much.
thank you, Dr. Subban, for presentation. I'd like to
Oh,
thank from the organizer side.
okay.
Yeah,
Thank you.
so
Thank you very much.
moving,
Yeah.
so moving to
Okay.
the session of
Yeah.
next session, we will
Next show.
have next of our chair, Dr. Nirmala Grace, who is currently position of a director at Center for Technology Research. May I, Dr. is here? She's here. Yeah. So
Yeah. Hi. Good morning.
we have our speaker. Can you please session?
Hello, can you hear me?
Yes, yes, we can.
All right, let me, okay. Yeah, all right.
Yeah. Hello, Dr. Prashant. Nirmala here.
Hi, Nirmala. Hi, how are you?
Yeah. Fine. How are you?
Yeah. Doing well. Yeah.
Great. Nice. So I think we can get started. The participants are waiting.
Yes,
Uh,
we can.
Yes.
yeah, we can get started. No problem.
Sure.
Yeah.
So good afternoon to one and all. It's a pleasure to have Professor Prashant Sonar with us in this wonderful conference. So it's my pleasure to introduce Professor Prashant. Dr. Prashant Sonar is ARC Future Fellow and Associate Professor in the School of Chemistry and Physics and Centre for Material Science at Queensland University of Technology, QUT, Australia. He was also appointed as visiting professor at School of Material Science and Engineering, Indian Institute of Technology, Kanpur, and he holds adjunct associate professor position with Griffith University, Australia. He performed his doctoral work under the supervision of Professor Mullen at Max Planck Institute of Polymer Research, Mainz, Germany, and was awarded his PhD in 2004 in Gutenberg University in Mainz. Dr. Sona moved to Swiss Federal University of Technology, Zurich, ETH, Switzerland, for doing his postdoctoral research with Professor Schulter from 2004 till 2006. And then he was working as a research scientist at Institute of Materials Research and Engineering, Agency of Science, A-Star, Singapore. Dr. Sona received prestigious future fellowship from the Australian Research Council and was appointed as associate professor at QUT, Brisbane, Australia. At QUT, he established Organic and Printed Electronic Research Group. Currently, he is serving as associate editor of the journal Flexible and Printed Electronics, Material Research Express, Frontier in Chemistry and Energies. Recently, he has been elected as Fellow of the Royal Society of Chemistry and Foreign Fellow of Maharashtra Academy of Sciences. Dr. Sona is interested in design and synthesis of novel pi-functional materials, small molecules, oligomers, dendrimers, and polymers for printed electronics like OFETs, OLEDs, OPVs, OLEDs, OPDs, and sensors, perovskite solar cells, bioelectronics, supermolecular electronic and wearable electronic applications. He has delivered more than 90 invited talks at various international conferences and institutes. He has authored or co-authored 155 peer-reviewed research papers in international journals with a H-index of 40 and total citations cumulating to 6,600. 6,300 and filed 9 patents and patent application in regional and international level. Recently, his 2 patents licensed to the multinational US-based company. So, welcome, Dr. Prashant Sonar. It's an honor to have you here, and may now request you to take over the session with your lecture. Thank you.
Thank you so much, Professor Nirmala, for your kind introduction. I will start sharing my slides. Just give me 1 minute. Where did I just it was open here. There are plenty of window. I just need to might be. Where it is, why I cannot see it here.
Sir, sir, excuse me, sir.
Just a minute, it is, I
File
can't
in the
see
presentation mode.
it
Please
here.
close that one and then open this.
Okay, I'll just close
Yeah,
it.
that's
So
yes,
should I
yes.
log in or?
No, not in logging, sir. You just remove the presentation mode of your file very first.
Okay, just a minute. Sorry. Okay, let me see, share screen. Now I can. Oh.
Yeah. Now it's working.
Now I can see. Yeah. Okay.
Yeah.
Okay. Yeah. Okay. Perfect. All right. Thank you for your patience, and it is as usual wonderful to be a part of VIT community, and it is always great pleasure to give some sort of our current research work, what we do in QT.
Professor Prashant, you are sharing your different screen. You have to share your presentation. Actually, you are sharing your folder screen actually.
Oh, really? Oh, just a minute. Huh? Okay. I thought that I shared it. Okay, stop sharing and then share screen again. And then, is it okay now?
Yeah, it is
Yes,
fine. Yeah.
yes.
Okay, all right. So today I'm going to talk about some of the recent work which one of my PhD student has carried out. His name is Hound Farm David. And first I'll just wanted to kind of show you, I don't know why to get rid of with this one. The slides, sorry, just bear with me. The icon which I cannot move it from here. Okay, now I can. All right, this is much better because it's keep on hindering my slides. Okay, I'm going to talk about the whole transporting material, and it's a kind of molecular engineering for perovskite solar cell application. Actually, the affiliation with the QUT, with the VIT started really thankful to your student, master student Suankar, who is now with me here in QUT, performing his master by research work. And he's really nice, nicely done a lot of exciting work. Today, I'm going to share some of his work where he kind of focused on some of the lead free stuff, which I will share you at the last. And I really wanted to thank also Nirmala and Raja Selepan. They kind of the main supervisor and co-supervisor from VIT side, and I'm kind of handling him here in QUT. So my research work in QUT, usually we do focus on various aspects. Particularly, my main intention is to design organic semiconducting materials. Those can be utilized for flexible, printable, stretchable, wearable type of materials and devices. And then the bioelectronic is upcoming one. You can see using some of this organic semiconductor, we can really make the thin films and we can print them, and that's why the reality foldable smartphone is reality, as well as for wearable smartwatches we can have this OLED screen, and organic semiconductor plays an important role as active semiconductor like emitting layer. Then stretchable electronics is another coming up where we can have this stretchable semiconductor. They don't change their charge carrier mobility or performance upon stretching, and that could have a lot of important application in wearable type of devices. Biodegradable electronics, which is another exciting research work. Recently just we kind of published a wonderful review article on this. Electronic waste is a major issue, and how to make this biodegradable film or devices which has a certain shelf life and they can be discarded in a nature without having any electronic waste issue, like what other kind of the electronic devices has that implication. And I started bit of collaboration with NTU Singapore. We got a project with them, and I will try to develop some biodegradable semiconductors for some of the transistor and other type of application. For OLED display, solid state OLED lighting, like having a white emission is still very critical. To get a single layer white emission, still there are not many materials exist, and TADF type of a new class of material where the brightness is a high, which we can utilize this external quantum efficiency can be enhanced by utilizing the 70% loss of this kind of the singlet triplet. You know that 25% we can utilize the singlet for emission, but the 75% they are getting lost that can be utilized by using this reverse intersystem cross-linking type of concept, and then we can make a TADF material. Then flexible solar cell, rollable display, self-filling material, and name of few, like some sort of like a smart kind of the lenses and all that. The molecular material plays an important role because we chemists can design the material which can control the homolumos values or charge carrier mobility based on their kind of a building block in the backbone, and those building blocks can vary from the cheap low cost high performance dyes, and we can make the kind of soluble inks, and then we can spin coat them. We can control their pi stacking distance. Their self assembly can be controlled what we are putting in a alkyl chain, I mean side chain, or in a backbone. And due to this kind of a nanomorphological aspect, we can really drive this performance quite high. So looking at this kind of a paradigm, or might be the expansion of my research work in QT here, we do work on OFED, OPV, and OLED, Perovskite, and other type of sensing devices apparently. And I mean, this is a very vast field. It can be integrated for organic photodetectors and other type of materials as well as the devices. And we are always kind of looking kind of various new opportunities, how we can utilize these devices for might be latest artificial intelligence or robotics. So I am really passionate about the dyes. Dyes and pigments are very close to my heart. And I mean, I have done a lot of significant work on dyes and pigments since my PhD days when I was in Mainz, Germany. And in Singapore, I did also a lot of work on a Ferrari red color dye, which is shown here. By taking this dye, we can really make high performance semiconductors. And there are other type of dyes, like particularly in perovskite solar cell, we picked up this vat orange dye, and another is a anthranthrone dye. Using this type of dyes, which we can kind of do the chemistry on them, and can be functionalized for making solution processable ink for perovskite solar cell. And some of these conventional dyes, which are very well studied, like perilene bicimide or naphthalene bicimide, and again some sort of other dyes which includes viologen or maybe anthraquinone type of. So those are really kind of a low cost dyes. Looking at this particularly, I mean, the type of the dyes which has a fused aromatic backbone, and that's what, because of the conjugation, we get some sort of a color as well as the emitting color, as well as they can absorb the photons, light for solar cell application as well as for display application. So particularly in case of a perovskite solar cell, looking at the current efficiency chart, which is taken from the NREL, and you can see that particularly the perovskite solar cell has taken a quantum jump in last particularly 5 years, let us say 2012, 10 onward. I mean, in last 10 years, let us say, it has really gone up very high. Earlier devices were very low performance efficiency. Still, I remember when the Henry Smith gave a talk in Singapore in ICMAT in 2010, I was just wondering what type of this perovskite material, and I mean, not much audience were there. But later on, upon looking his research work as well as the current growth, unbelievable. I mean, perovskite is one of the now one of the most outstanding material. But there are some challenges of this material, particularly the stability is a big issue because perovskite is nothing but organometallic type of halide. And as you know that organometallic halide means halide having the halogen, so which is a bit of ionic by nature, and the ionic compounds or such type of halides may have kind of propensity to degrade once we expose them to the moisture. So to avoid this degradation or moisture penetration to the perovskite layer, if you look upon the energy level kind of a diagram, or might be the device configuration. So in device configuration, we do have an anode and cathode. These are the two electrodes. In between that, we sandwich the perovskite layer, which is a light emitting, light absorbing layer. We can also use light emitting perovskite. LEDs are also well-known topic nowadays. The perovskite can absorb or emit light depending on its band gap. Particularly in case of a perovskite solar cell, once you shine a photon on it, exciton formation happens. And one of the beauty of perovskite material compared to the classical organic semiconductors is that in case of organic semiconductor, your exciton cannot travel a really long distance. They can might have a 20 nanometer of exciton diffusion length. But in case of perovskite layer, exciton can travel up to the micron level. And that is what the efficiencies of perovskites are quite high. And if you can make a thick devices, still device efficiency is quite good. That is not the case in case of organic solar cell. So once you shine a photon, then photon gets, once photon kind of bombarded on a perovskite layer, it forms exciton, hole and electron pair. This exciton gets then separated via hole transporting layer, holes goes, and electron goes via electron transporting layer, and respect to cathode and anode, we get the free charges, and those charges can be collected as a current. This is a simple principle. So ETL and STL, which is a hole transporting layer and electron transporting layer in between perovskite layer sandwiches, and we can really protect this perovskite layer by kind of having appropriate ETL and STL. So roll up, particularly today, I'm going to talk about HTL. We also started a bit work on ETL. Might be in future I can present that work. We just got some initial device results, but today I'm going to mainly focus on a whole transporting layer. So what is the kind of some sort of a role of the whole transporting layer? First of all, whole transporting layer not only protect your perovskite layer underneath, but also it assists for whole transport and also blocking electron movement depending on the HOMO value. It really helps a lot to kind of dissociate the charges which are forming in perovskite, because until unless we don't have a whole transporting layer, efficiency can be limited up to might be 14 or 15%. So in order to push this efficiency down and to collect the most of the charge carriers, we should have this whole transporting as well as electron transporting layer. Then it protects perovskite layer, which is good for in terms of the enhancement of stability from moisture and all. The main principle while designing the low cost whole transporting material, we should have a straightforward synthesis, which is very important. As you know that spirometad, which is a commercial available, most of the researchers use that material, which is very expensive, $350 per gram, whereas the material which we wanted to synthesize should have a simple synthesis. It should have a simple purification and can scale it up on a large scale. And importantly, its HOMO value should be close to the HOMO value of standard methylammonium lead iodide, which is a 5.43 electron volt. But again, we can tune this HOMO value of the whole transporting layer depending on what type of perovskite layer you're using. If you're using mixed halide or other type of a perovskite, which we can really tune the kind of a suitable whole transporting material accordingly. Then it should have a high solubility in common organic solvent like chloroform and dichloromethane, and at least until unless our HTM shows efficiency higher than 15%, then it is a really meaningful to have a HTL. Otherwise, without HTL also there are some reports people can get efficiency 15%. So our benchmark is to kind of have this particular kind of design principle. So looking at the kind of the various whole transporting material people are using. Mainly I mentioned to you spirometad. Whenever people use them, they usually add additives called as a tertiary butylpyridine, as well as they add the lithium based trifluoromethane sulfonamide. So this, because of addition of those two additives, the conductivity of spirometad gets high, and that's what it can be a better whole kind of a transporting layer. But again, look at those materials. They are some sort of lithium is also kind of a salt by nature. Your perovskite is also organometallic halides, bit of ionic compound. So you are making the whole system very vulnerable to the moisture. So and again, looking at other type of materials people use as a whole transporting, particularly polymer, PTA, triphenylamine, which is a very expensive material, even 10 times expensive than the gold. And then we have a P.PSS, which is a polyethylene diacethypene polystyrene sulfonate, which is acidic by nature. And utilizing those P.PSS and PTAA, our kind of the the whole system becomes highly kind of vulnerable to the moisture, because I mean it is ionic as well as acidic by nature, the T.PSS polymer and the spiro. So our novel STM should be low cost. It should have eco-friendly, high efficiency, durable, and I mean, as I mentioned to you, have a high hole mobility and dopant free. We do not want it to add this lithium type of dopant. We should have material which can be dopant free. So first we checked upon the one of the dye called as anthranthrone. I mentioned to wet orange. It is a very nice fused aromatic moiety. This dye we can get commercially very cheap, like $200 in Australian dollar per kg, very cheap. And then using this 2-bromine, we can do some chemistry, and we do also have this ketonic group here. We can do some functionalization, and look at that. It is a very planar which has a 6 benzene ring, very flat aromatic core, and it has a good pi-pi intermolecular interaction because of this flat nature, as well as benzene aromatic rings are there. They can stack very well, and it has also high hole transport property. So first we took up this dye, we end cap that one with a diphenylamine. This is a commercially available, we synthesized the diphenylamine with methoxy substituted one. And then we use another end capping group called as a dimethoxy again substituted triphenylamine with the boronic ester. So this boronic esters with the bromine combination makes the whole system like this 2 molecule called as a Suzuki coupling. Once boronic ester and bromine combined together, that is Suzuki coupling protocol. Whereas this amine group attached to the bromine, that is called as a Buchwald coupling, we can make a 3 compounds out of this starting material. So initially we just throw this material with this, and we got a STM1, then we got STM2 and 3 by using this end capping group. This type phenylamine is a very well-known end capping group, but this end capping group was discovered by us in QT. We were the first to utilize this. It is a bit unusual compound, not many people have looked at. So we thought that it has a naphthalene, similar like having benzene, you know, that aromatic, they may speak nicely, and they may have a good kind of, the stacking as well as good solubility because of this cyclic ring. And synthesis is pretty quantitative. We get a very, we can make these compounds in a gram scale without any issue. And looking at this compound and their energy level, usually to calculate the HOMO energy level, there are various techniques people use, like cyclic voltammetry is one of the very common and low cost technique where you have a HOMO-LUMO value can be determined by oxidation and reduction onsets. But again, in case of a cyclic voltammetry, the biggest drawback is your material need to be dissolved in a solution, and then you get those, the values. Sometimes those values are in a solution, might be not relevant to the actual device where the device is in a solid state. So the technique called as a photoelectron spectroscopy in air, which is a very straightforward and nice technique. I was fortunate enough to get knowledge of those type of the technique when I was sorry, can you hear me?
Yes, Prashant, yes.
Yeah, sorry, I thought that I got some message. Okay, so utilizing these HOMO values, looking at this using PESA technique, if you see this particularly 3 molecule shows the HOMO value 5.4, 5.3, and 5.41. So just as an end capping group and the core, we can tune their HOMO values and look at the LUMO values. The LUMO values of this material should not be close enough to the LUMO of your standard perovskite. Otherwise, they may have a ability to transport electron as well. So particularly STM2 and STM3, they are quite far from the LUMO value of perovskite. And again, comparing this one as a standard mesoporous TiO2 here, I just showed the energy diagram. So when we utilize these 3 out of these 3 material, when we utilize them like last STM2 and 3, we got a very high performance, where STM1 has a bit of average performance. But here is like the standard mesoporous device configuration. Instead of spiro, we utilize this 3 material in this device. And the whole mobility of this material, you can see that all of the 3 material, the highest the hole mobility which we got for the TPA and TTPA, which is a 2.6 into 10 raised to minus 4, whereas the Spiro shows 1.5. So almost we get to double the hole mobility compared to the Spiro, which is a pretty good news. So first, looking at the one compound STM1, which is a simple compound, and we thought that we have a donor acceptor donor type of molecule, and we can kind of see what is the effect of this donor acceptor donor type of conjugated building block. And here we kind of get the efficiency 10.8. This was our first kind of devices, and comparing our STM with the Spiro devices, I mean the highest efficiency we got 11.5%, whereas Spiro shows still 16%, quite high. But one of the important aspect that our kind of the material shows better stability than the Spiro. Looking at this, these are the kind of data comparing with the diphenylamine and ANT, DP, ANT, and with the Spiro like IPC curves, and that shows like current value we still get little less compared to the Spiro. But in another slide you can see, upon looking this kind of STM and putting them in a mesoporous titanium dioxide exactly same like a device configuration, we could determine the contact angle for the just using our material, the I mean the Spiro one, which is a commercially material, which shows 47.97 as a contact angle without any metal, just perovskite having 21.75. But upon putting our newly synthesized material DPA and TDPA, contact angle really goes quite high, almost close to 100 degree, which is like which is very good in terms of enhancing the kind of a stability, because water cannot penetrate in due to the high contact angle. And here is the device kind of the degradation mechanism, or might be we can see how device kind of we can see taking the fresh device and aging for 57% relative humidity for 50 hours. So our power conversion efficiency from 11.5% drops to the 10.3, whereas in case of a Spiro based device, it has gone all the way from 16 to 2.3. Very lousy, very immediate degradation. So this clearly gives an idea how contact angle of these STMs are important to enhance the stability, and we get a very significant low degradation, whereas in case of Spiro, degradation is high, and that is might be obvious due to the I mean low contact angle, as well as some of these ionic additives they use while fabrication of the devices, which I mentioned, like lithium and all those type of additives. Taking these other two compounds, we made the solar cell, perovskite solar cell devices in collaboration with Sagar Jain in Swansea University. And the highest efficiency which we could achieve for the one of the compound called as a STM3, which is a TPA and TTPA, which get almost 17.5%. And the cost of this TPA and TTPA is $67 per gram compared to the Spiro, which is $91. And this is the like commercial, I mean, price which we determine by taking all of this, starting material into an account. So these are the dopant-free two materials, and we can get a really high efficiency. The Spiro, just for the comparison, we have to add the dopant lithium, this TFSI, TBP. I mean, efficiency-wise, still lower than our devices. And looking at again the fresh device versus the kind of aged devices for 10 hours, you can see that in case of our newly synthesized STM material, there is only 20% loss, and I mean from 17.5% we get a 14% efficiency with a relative humidity of 58%. Whereas in case of Spiro, which is a commercially material, very expensive material, which has a contact angle 47, in our case contact angle 85, they see this 86% kind of degradation. So this clearly indicates that our newly synthesized STMs has a much better stability, and I mean they can long last. We got kind of as a Wiley video, abstract accepted. I think because of time I may not play this one, and also might having issue with listening, but we also got featured on a channel 7 News in Australia. Energy minister visited our lab, and we got a lot of attention of this work because the low cost and using this orange dye, we can make really the high hole transporting material, and as well as we filed a patent on this. And that yielded up, here is the conclusion of those 3 STMs. We could achieve really the high efficiency 17.5% among out of these 3, and the PC degradation is only 20% in case of STM3, whereas 10.3 for STM1. And we got a couple of papers on that, one in advanced energy material and another is a general of material chemistry, and there's also filed a patent. So we picked up the another dye, which is a quinacridone dye. And this quinacridone dye then again, it has this ketonic group and alkyl group, which we can utilize as a solution processable motif like octyl group. And then again, taking this end capping group, exactly the same, only we changed the dye here. We took a quinacridone. In earlier case, we have anthranthrone. This one is a more like the cyclic aromatic ring, similar like a pentacene kind of, having 3 benzene ring and some cyclic ring with a nitrogen and ketonic group. And upon doing Buchwald coupling, similar like bromine with NH, which is a Buchwald, boronic ester with bromine, that is Suzuki coupling with standard catalyst and all the synthetic aspect there, we got this 3 compound. And looking at this 3 compound, again, you see the HOMO values are quite low, 5.59. Usually if HOMO values of 5.1 or might be 4.9, they are not good because they may have a high ability to oxidize because of the very high HOMO. We got a very low HOMO. That is really one of the striking feature of this new STM, how we can get a stable performance. And they're also matching well with the standard perovskite HOMO value 5.46, and again it has a LUMO values kind of not that close to the LUMO standard perovskite. Looking at these 3 materials, we got now this time efficiency again 18.2% for one of the compound. Now we have moved from 17 to the 18.2, and look at this. In this case, now the relative humidity is much higher than the earlier case. In this case, is 75%, and still you can see how STM 4, 5, 6. These 3 compounds are stable compared to the Spiro. These are the kind of IPC data as well as JV curves, and we can really get a very high short circuit current, close to might be 22.0. That is one of the highest one. But I mean, another device where we got like open circuit voltage of 1.06, we got really high efficiency of 18.2. And I mean, again, these are the dopant free kind of a 3 STMs, and we published that in a Journal of Material Chemistry. Then we come up with another interesting molecule, which is slightly, I mean, we can say it is an emitter as well as it is a nice STM. And here we took up the this fluorine as a central building block and triphenylamine end capping group. So in this case, what we did, we put this triphenylamine like methoxy substituted at the 2 and 7 position, whereas this triphenylamine at this particularly 9,9- position of the fluorine. And then we did the reverse structure where instead of putting this 2,7 position, we put them on a 3,6. So these are some sort of a geometrical isomers kind of a molecule. Just by changing the position from 2,7 to the 3,6, how the performance changes. And that was kind of one of the question we ask ourselves. If we just have a little bit of molecular geometrical change, how we can tune the performance? Now this time we utilize these devices using the inverted devices, similar like organic solar cell type of ITO coated glass with molybdenum oxide. Then our molecule, they synthesize, then we put up this methyl layered ammonium iodide. Then we put up the C60 fullerene as an N-type material, then DCP, another kind of electron transporting layer, and then silver as a top electrode. Molybdenum oxide is a whole transporting layer here. And then upon looking the device efficiency data, now in this time also we can achieve like 17% efficiency for this compound for the 271, whereas in case of 37 we got a 13 point, almost 14%. See, just by changing this position, there is almost kind of a difference of 4%, and that clearly indicates that how important is molecular geometry or engineering. This was published in again JMCA, and I mean, I'm just showing you just a snapshot of this work where we got the again open circuit voltage of 1.05 and PC of 17.1 with a very high fill factor. Then we made another material. We took up this dicyano kind of a core with a bromine at the end. And then this triphenylamine, we encap this one. We got this TPA, BPF, and TPA. We got, I mean, usually we do for all of the material optical optical absorption, where we calculate the band gap by taking cutoff values, and then we get the HOMO value by PESA 5.47, and then looking 5.47 of this STM with Spiro comparison and LUMO, we get the cross section of this standard mesoporous devices. Again, using this dicyano device without having any additives, these all are dopant free devices. Here we can achieve the efficiency 18.4% and open circuit voltage pretty much again more or less more than 1 volt, and then short circuit current. And these are the kind of the IPC and JV curves. Again, the stability data. In this case, now we could push the contact angle up to 112. In earlier cases, we got might be 80 or 100. Now this case, we got really highest contact angle for the TPA, BPF, and TPA. And it could be the reason some sort of the what conjugated backbone you're putting up. If you have a bit of highly aromatic and very non kind of ionic type of moieties, or might be which are inhibiting water penetration, we can really push these values. And then these are the standard solar cell condition 1 sun, which we called, but we also tried to do some of this perovskite solar cell work. I mean, Sagar tried to do the low light condition, because not necessarily when people think about solar cell means they should be on a rooftop. They can be also have an indoor application. And for indoor type of application, if you do have a illumination of, for example, let us say 100 lux with a low light intensity, we can achieve very high efficiency, 30% and 22% for this kind of a standard Spiro device, comparing with our newly STM fabricated devices, 30%. So here is also clearly seen that with low light condition, these devices works very well, and we got very high efficiency. So I mean, whenever the perovskite solar cell community, they should also think about this indoor solar cell and how the performance can be obtained high with the low light conditions. So might be not really many people have done that type of study. So we thought to kind of explore those opportunities there. And it was published in Advanced Electronic Material. And this is kind of a conclusion, STM7, which gives the 18.4% one sunlight condition, and with like 100 lux condition, we get 30%. So I'll jump on to the next. I do have another 10-15 minutes, Nirmala.
Yes, Prashant. Yes, you can proceed.
Okay. Okay, good. So this is a 45-minute talk, which is a great. I like that a bit longer talk rather than the shorter talk. Otherwise, we don't get a time and I have to rush. So we also kind of come up with some of the other type of the conjugated cores, like anthracene, and then the thiopine vinyl thiopine, and then naphthalene, and then dithienothiopine, naphthalodithienothiopine. These are some of the building block we utilized earlier for making the high mobility materials for transistor application. And we thought that if this molecule shows a very high mobility in transistor, can we explore them as a whole transporting material for perovskite solar cell? And taking this central building block, we put up all of having the same kind of, the same end capping group, only we tune from like 5-membered ring to the 6-membered closed structure like naphthalene, to the more closed structure, and then little longer acenes, and and then in this only the last case we put a diphenylamine, whereas in all these 4 cases we put the triphenylamine with the 3-phenyl group with the nitrogen. Here are the 2-phenyl group with the nitrogen, and we analyze all of these 5 compounds. So these are the kind of HOMO values of all these STM 9 to 13, 5.38, 5.37, 27. 5.40 and 33. So again, depending on what you're putting, if you're putting electron rich kind of a core, which is electron donating, your HOMO value gets a bit high, means they can be 5.27. If your inner moiety is electron accepting or might be little electron rich, then your HOMO value gets lower, like 5.3, 5.8, 38, or maybe 5.4. So that really we can tune those things according to the building block what we put in a conjugation. Looking at these all HTLs, the power conversion efficiencies values are given here. We compare that one with also P.PSS in one of the cases. I will show you shortly. But I mean, we got like 16.32% kind of highest efficiency. But again, I mean, this work when we did that time, it was kind of the very start. My PhD student when he started, and this was like a warm-up activity, some sort of to get a new molecule and how kind of the we get the performance. So in this case, we use the additive with perovskite and our HTM. In this case, they are not dopant free. We added the dopant, and we try to see the performance. And in this case, like I'm just showing you some J because of this particularly TPA, TVT, TPA, this particular one compound, and looking at this value and comparing that one with the naphthalene here, how this quenching efficiency, quenching efficiency changes based on this PL quenching data here. So that clearly indicates that if the quenching is quite high, it means that there is some sort of a good communication between our interfacial layers. Yeah. And here is the comparison of these two molecules, and we got like 16.32%. We did also stability study, although these were with that. Sorry.
Sorry for interruption. Please go ahead.
Okay, so we got the contact angle measurement, or P dot PSS is a highly polar polymer, and you see the contact angle is very lousy, whereas our material we get quite okay contact angle. I mean, these are again, don't compare this contact angle with our earlier molecule were too good. These were still with additives. That's what the contact angles are low. And yeah, but again, we got a cover picture for this one. Here we demonstrated that using this TPA, TVT, TPA type of the kind of whole transporting material in inverted devices, which we can get this type of efficiency. And this one was like kind of a very high VOC as well. Then looking at these two other molecule with phenylene, vinylene, phenylene, and biphenylene, we could get, again, in this case, we did the similar whole extraction efficiency using this time resolved photoluminescence, and where we can see in case of a TPA, BPV, TPA, which is a 30 nanosecond, whereas a TPA biphenyl TPA, which is a 44 nanosecond. It means that BPV molecule has a high ability to kind of, the whole extraction ability. So it might be the better material compared to the BP. And indeed, upon looking, BPV has shown the efficiency here, which is a 16.42, whereas BP has shown 13.27. Based on this whole extraction efficiency data, this clearly indicates that BPV has a better ability. And these are some of the forward and reverse bias. So very nice curves, no really hysteresis. If the devices are a bit of trapping and all, then we can see some hysteresis. But in a forward and reverse bias, we get a very similar type of a behavior. We also studied the surface morphology of interfaces. I think, and I'm also a stability test upon exposure to the 10 days, Spyro really degrades fast, whereas our devices stay still longer. And then these are the percentage stability with comparison. But again, I mean, these are with the dopant still quite good. So this one, like we got the highest efficiency around 16.42. This was published in, again, advanced electronic material. So then we took up the some of the other, remaining three molecule, which I showed in first a couple of slides. We utilize them as a whole transporting material, as well as we utilize them in OLED devices. So these OLED devices, we utilize them as a kind of a dopant, as an emitter with the host material, and we can really tune their emission efficiency. The values of emissions or OLED data is really not that bad. I mean, having like the getting these values of candela per square brightness in 18,600 is really quite high. And then again, look at the turn on, I mean, voltage of those ones are 3.8, very low turn on voltage. As well as we get a very narrow peak, like FWHM means full width half maximum, means we get a nice narrow emissions. And our emissions can really tune based on these backbones. And the same material we utilize as a whole transporting material. So it is as a dual benefit. The same material can be used as a whole transporting as well as emitter. And that's what it got in a JMCC, where we demonstrated the both type of devices. Efficiency wise, they are not that high. The highest one we can get 10.27, but we demonstrated also in OLED, and that was the reason. So it's like some sort of a versatile nature of some of the molecule, we can do the multifunctional devices. Neil is another student. I think because of time, I'll just skip. He invented a new dye, which is a naphthalene substituted DPP dye. And using this alkyl chain modulation, we got, I think, some transistor data. I will skip that. But this dye, look at this structure. Once we have a short alkyl chain like hexyl and octyl, we can really grow wonderful crystals, and these crystals are nicely emitting. And those crystalline material can show very high hole mobility up to 0.125 in transistor. But also we tested them in a perovskite solar cell, and then we could reach efficiency in a very high regime of 23%. But again, these are the one-time data. I'm chasing the Sagar to get much more thorough data, as well as we need to maybe certify these numbers as well to get really the reproducibility. This is like one-time device data, in which I think Sagar was kind of my collaborator, has moved from one place to the other, and still we need to get work on this. But I mean, we are working on this. Again, further in-depth analysis of those materials, and looking at the stability, initial data shows they are quite stable as well. So we utilize the same material for OLED devices as well. This is OLED kind of a device geometry. I think I'll just keep that one. I think I just will show you a couple of slides, and then I will be done with my talk. So here are some of the kind of important review articles we published recently. If you are keen to understand about the interfacial materials, particularly hole transporting, electron transporting, organic, inorganic, this is really nice review to read. So please check it in Energy and Environmental Science. And then another review where recently in Advanced Energy Material we published, where we are mainly talking about the dopant-free hole transporting material and how this technology is useful to make the stable devices. And there are like very few materials, they have ability to perform high efficiency without dopant. And these are some of the Suankar's work. I think we wanted to really work on, I mean, he took up a really hard project. I told him, Suankar, this is bit a PhD type of project, even PhD student cannot achieve, but he took up that challenge. And we got some learning, but not up to the mark where we can utilize these materials in devices. He made some lead-free materials because the lead is one of the biggest kind of the challenge in a perovskite solar cell community, how we can get rid of with the lead. And Suankar had given this problem of making the lead free. So he make cesium tin iodide type of this material. He got ACN data and all, we got a HOMO value. He faced the problem of making devices because these are the very hard organometallic halide, doesn't have ability to form a nice film as compared to the other perovskite, like I was showing you, the methyl ammonium lead iodide and all that. They have organometallic. It means they have some methyl or might be some alkyl group there. They have ability to form a film. But if you remove the alkyl group, these are the pure inorganic halides, like cesium, tin, both are inorganic, and iodine. There is no any organic component. So they are very hard to get a kind of, thin film, and that was one of the biggest challenge. He made plenty of solubility and thin film optimization, and he spent significant time. I also learned some other time of flight measurement to determine some sort of a component of cesium and all. There's some of this emitting material which we are now trying to synthesize and try to utilize in LED devices. With this, I will stop here. I'd like to thank Hong Duk Pham, one of my PhD student who graduated. He really did a wonderful work. Today's most of the work is complete PhD thesis. He might be 15, 20, he might have synthesized 15, 20 HTMs. We published 14, 15 on other, still we are writing papers. And I mean, yeah, he is working in QT on a battery project now. And with this, I'd like to thanks for your kind attention. This is my group, but this is the old picture. I need to get the new picture. I think out of 6, 7 students, almost 5 students are almost graduated. So a couple of are staying with me. Other three are they join in other groups or they move for the postdoc. So yeah, I think that's it.
Yes, thank you, Prashant. It was really a wonderful presentation as usual. So a few questions from the participants. Let me ask you. One of the participants has asked, please explain the role of hydrophilic and hydrophobic nature regarding to stability.
Role of hydrophilic and hydrophobic, sorry?
Yeah, hydrophobicity and hydrophilic and hydrophobic nature of
Yeah.
materials regarding to the stability issue of
Oh yeah,
perovskites.
this is a very important kind of question, and the whole perovskite community should understand this one. Hydrophilicity and hydrophobicity is depending on the nature of the molecule. I mean interfaces and various type of materials which we are using in a perovskite solar cell. In case of metals and all, they are no problem. But whenever the perovskite layer comes, which has this lead ammonium, methyl ammonium lead iodide, lead and iodine having Pb plus and iodine minus kind of ionic type of a system, I think it becomes a little bit a bit of vulnerable. And once moisture comes in a picture, the integration or might be the kind of affects performance so badly, and that is the reason how we can make this material which are hydrophilic or hydrophobic. So hydrophilic means water loving, hydrophobic means water hating. So making hydrophobic is only the way to make them hydrophobic. You have to put heaps of non-polar group in a backbone. If you have a very long alkyl chain which are very non-polar, then your material can be hydrophobic. If you have a polar group, like might be some sort of a carboxylic acid type of functional groups, or might be esters, they are vulnerable. They attract water very easily. And if your whole transporting layer or electron transporting layer have those type of ionic building blocks, then your system becomes highly hydrophilic. So making hydrophobic system is really very important for stability. And you notice from our data, as well as there is a lot of work going on that line. You read that might be dopant free. Our review article there, we have clearly mentioned that how water degrades and then how because of water the performance affects in a clear mechanistically way. You can read upon. Yeah.
Thank you, Prashant. The other question, two-dimensional 2D perovskite single crystals have attracted a great interest in solar cell applications due to their excellent crystallinity, phase purity, longer lifetime, etc. What is your view on single crystal?
Oh yeah, I think single crystals and all, really they are absolutely fascinating materials in terms of performance wise. We really cannot compete crystalline material with amorphous or semi-amorphous material. One of the biggest problem with the highly crystalline material about this is a trade-off. If we have a very highly crystalline material, either to process them on a large scale is a big challenge. This is also the same applies with the transistor community. Single crystal, wonderful. We can get a mobility 40, 50, like rubrine is a classical example. But can we make, it is possible to make a transistor array for might be OLED display with a rubrine type of single crystals, because handling these crystals are a bit of, sensitive issue. And again, they are anisotropic in terms of the performance may change in orientation or direction. So handling crystals, they are wonderful materials in terms of the fundamental science, but if we can able to make this crystalline material kind of throughput printable on a large scale, might be that has a extremely bright future. But how and to make them, that is one of the challenge, and that might be the open for community. So definitely 2D material has attracted a huge attention, and I think most of the work recent times in OLED LED community as well, perovskite LED, they're looking like 2D material as one of the very important component. So absolutely I agree, 2D material has a huge, lot of potential. Just need to resolve few of this issue. And again, looking at this interface between 2D and 3D, we need to also look upon like whenever you take the 2D and different STL or ETL, whether the interfaces have a better kind of a communication. Sometime if you take a 2D as active layer, and then you have some of the material which are like Spyro is a bit of Spyro shape, they might have not that great communication. And it has been also revealed by some publications, like they took 2D and 3D versus Spyro, and then they could see that 3D works better because your STM and your 3D Spyro or your 3D Perovskite, they speak nicely and they have a better charge transport separation mechanism and all. Whereas in 2D with Spyro STM, there might be issue. So it is like if you change the 2D, then you have to change the whole other interlayer as well, ETL and STL as well. So you have to do this all permutation combination. Yeah.
Sure. And there's one question, why particularly methyl ammonium lead iodide, MAPBI3?
Why lead ammonium, methyl ammonium?
Methyl ammonium, yeah.
Star molecule?
Yes, yes.
Okay. I think it is
fundamental question.
Yeah, it is. I think the reason is simply because it has been a lot of work has been done on this molecule since beginning. But I mean, people tried various alkyl tuning methyl to the ethyl propyl, or might be even changing from lead to the other type of the metal component in it. But I think somehow this lead methyl lead ammonium iodide has that kind of a combination in a way that it might have as a default, it is a very nice ambipolar material. The one is like it has a very high exciton diffusion. It means that the exciton can really migrate nicely on a long micrometer scale. Third one, it has a good kind of a film forming property because the organic component coming in a picture like methyl group, and it is very easy to synthesize. So a lot of attention has been given on this molecule, and also has a very high charge carrier mobility and all those. Also in terms of looking, if you change some of the, instead of methyl might be other, if you just remove the lead, and people have been trying lead free perovskite, they can't reach efficiency more than 5-6%. So somehow it is related also with the lead material that might have a high absorption coefficient, or photon flux is really very high. Other material may not absorb that photon. So it might be related with the molar absorptivity of the material. So all of these figures are, all of these parameters are ticking this molecule, and that's what is a star molecule. So yeah, whatever the features are required for the best solar cell efficiency.
I think that has been now used as a standard one. Yes. The one last question, Prashant, is your contact angle high? And if that is the case, it might be difficult to get a good uniform film. I think by Dr. Ramesh Tamankar.
Sorry, I didn't get it.
Is your contact angle high? And if that is the case, it might be difficult to get a good uniform film. So is that correct?
If the contact angle, sorry, Nirmala, can you repeat again?
Yes, yeah. Is your contact angle high? And if that is the case, it would be difficult to get a good uniform film.
Good what?
Uniformity in the film. During
film. Good uniformity in the film. Contact angle and uniformity are a bit of two different aspects. I mean, contact angle is more, definitely they are related with each other. But again, if you have a not really a good quality film, your contact angle definitely can change. You are absolutely correct. If you have a better film forming ability, then only you can have a better and then you can then probe in some cases like the contact angle may change if you have patches of the film. So whenever whenever we make this contact angle measurement, we make sure that our films are uniform. If we get a patchy film, it is hard to measure contact angle, because I think in some cases your underneath substrate is getting exposed, and might be other side you have your STM, so it may, the water may kind of repel at one side and it may get attract other side, so you may not get appropriate contact angle. Yeah.
Thank you. Yeah, yes. Thank you, Prashant. I think for want of time, let me close the session. So thank you once again, Dr. Prashant, for such an interesting session. And it was an honor to have your presentation lecture. Thank you.
I'd like to thank all of you, as well as my friend Ramesh, who is in audience. He gave me invitation, and really thanks for getting this opportunity, and looking forward many VIT students, they should come to QUT, and QUT VIT also has a joint kind of a MOU. So hoping for the many more students and much more engagement with you guys. And
thank you, Professor.
You guys are doing awesome job. Okay.
Thank you. Our pleasure. Thank you.
I would like to thank both the Professor Prashant and Session Chair Nirmala Grace, who agreed our request to come and hold the session and give the talk. With that, I would like to invite Dr. Rajan Babu if he has the closing remark for this session. Dr. Rajan Babu, can you?
Yeah.
So if you have any closing remark for this session?
Yeah, the next session starts at 2 o'clock. No, 1 hour lunch break. We will continue at 2 p.m.
Yes.
Thank you.
Thank you very much. Thank you, madam,
Thank you.
Bye, Prashant. Yeah.
for chairing the
Bye
session.
bye. See you. See you.
See you.
Thank you.
Bye. Have a nice day. Bye.
So, Professor Ramesh, you want to say anything?